Okay, so just like for the big step semantics, we're going to study the properties of the small step semantics. And we'll start with the notion of final state, right? So we would be interesting to know, so final state means you cannot take any transition from there anymore. And of course, if you are in a configuration where, so not a final state, but final configuration, if you are in a configuration where the first component is skip, then you know you have a final state. There are no transition possibles from there, and that's easy to prove. But the bigger question is, are there other statements that maybe under some conditions could lead you in such a situation? You know, for example, if you take the else branch of an if, is it possible that you block there, right, with nowhere to go? Or that you get stuck after 10 iterations of the while loop and you cannot continue the loop and cannot exit the loop, or something crazy like this, right? So we want to show that this cannot happen. So we say here basically that if there is no, this says, right, there, the configuration SS is final. That's how we write it mathematically. There exists no configuration TT prime, you know, that, you know, you can go to from SS. If and only if the big S is skip, right? That's the only condition, the only case where that can happen. And in that case, it happens. That's why it's an if and only if. And this is what the proof looks like. We do a structural induction first on S. And again, it's not always obvious. Why do we do that instead of doing something else and so on? I cannot even give you the answer right now. I know that this proof happens to work, but maybe you could start by, you know, splitting the if and only if, and then you do both directions separately and you do other things. I guess it would be longer, but I don't know. I mean, there are often several proofs possible, and this is just one that works. But I mean, I must say even experts at proving don't, you know, they don't always know which induction to do in which case. You have to play a bit with it and follow your intuitions and see where you get stuck and so on. That's part of the game. That's really what theorem proving is about. We cannot give you rules, and we cannot tell you just follow these rules and everything will go fine and you'll be able to prove anything, right? It's always a bit of a challenge. Okay. So, and then we end up with various cases. I'm not going to go very deeply into that proof, but again, we have 5 cases because there are 5 types of statements. And well, in the skipped case, we simplify, and we then we end up with for all. We can do 3 intros here, right? Okay, that looks already better. And basically, it says if you can make a transition from skip, then I mean, then you have to be able to prove false. We just do a cases on H step, and because there are no introduction rules in the predicate that have skip here, right? There is no rule for skip, as I've asked before. Just doing that will eliminate all 7 cases because this matches none of them. And then you have 0 cases left to prove, and it's game over. And if I put a comma, then I see that it's game over. Okay, and then there are a bunch of other cases. I'll just show one interesting idiom, I think, which is in the if then else we see it among other places. But first, again, we have this monster. We simplify it. Already looks much better. And then the trouble is we have to exhibit, you see, basically a configuration called XX1, not the nicest names, but okay. You know, so you have an if then else, and you have to be able to go to that configuration. And the problem is we don't know if B is true or false, if the condition is true or false. If it's true, then we know where to go. We go to S, big S. And if it's false, then we go to big T, but we don't know, right? And the state X, so X1 is going to be S for sure, because the state doesn't change when you just take one branch or the other. So here we can do a case distinction on the condition, and that's the idiom we've learned with classical EM. So I think that was in lecture 4 or 5, 4 probably. No, 5. Inductive predicate. And if it's not 5, it's going to be 4. I promise you. And okay. Then we end up with two cases, right? The left case and the right case. So the true case and the false case. And then in the true case, we take big S. In the false case, we take big T as the witness, and this is the other witness. And then we apply if then else true, the introduction rule for, in one case for true, and the other case for false. That's how we deal with those cases. And it's a bit the same in, you have the same in sec, because there are two rules related to sec, and then you do a case distinction to find out which you want to take. So yeah, I think the proof was written like this because I didn't want to break the if and only if. I wanted to prove it only once and not twice. But then the problem is that there's a mismatch between the syntax for language, which has 5 cases, and the rules where we have, I think, 6 or 7. And then we have to have these case distinctions to kind of repair the mismatch so that we apply the right rule at the right place. Here I should mention we don't absolutely have to specify the witnesses, at least last time I checked, because it will replace them by these, question marks, and at the end when we apply the rule, it just they get filled in automatically. So here I put them more for documentation, and I mean sometimes good practice. It's I mean you have more control over your proof when you proceed like this. Okay. There's also proof of determinism here, right, which is similar to what we've done before, but we have a configuration LL and a configuration RR. We have to show that the two are the same because they both come from SS. And this proof I'm not going to review except to show 1 or 2 interesting things in it. And the first is here. So here we have an induction hypothesis again with one of these variables. Here's RR. And sometimes we know already, oh, I want to instantiate this with something, or in particular not the variable so much, you can even pass this whole condition here, and that is going to be HS2, right? Because it's going to tell us that S1 equals S2. So the one trick to do it is with a have, right? So we just do the have like this, and then we see what we get before we apply it. It just appears here, and then at that point, if we want, we can clear H. And I don't know why it's so slow. And now it's gone, right? You can clean your state like this, and keep your sanity, because there is sometimes quite a lot of hypotheses and constants flying around in the context. There's even a command called the specialize tactic, which does the same that as I've just done, if I remember correctly, except you see it reuses the name IH for the new version. So this one we normally don't teach because you can easily simulate it with the tools that you already have. So that was the first trick I wanted to show. And then the second one, well, this is something we've seen before already, that we can end up in impossible cases, where one condition is true and the other condition is false, and then we can use CC for, discovering that contradiction. But otherwise, it's similar in flavor to the previous determinism proof we did. And then there's a bunch of inversion rules, which I'm just going to scroll over very quickly. But again, these are nice exercises. Then at the end of the file, you have 2 optional sections. So first, there's the question of equivalence between the big step and the small step semantics. So there's a proof. I will just show the main lemma. It's somewhere where there's a lot of stuff here. Here, so big step if and only if small small step. So you have you can make this step if and only if you can make that step. That's what we saw already in the comment. upstairs, but now we've actually proved it in two parts. So this is one direction, this is the other direction, and it's using, you know, lots of fancy things we haven't seen, like this induction H using head induction on and so on. So it's a more complicated proof. But again, I just want to show these claims that we make, you know, that they're the same. We can actually prove them if we want, and this is the proof. And then there's an optional section at the end about parallelism. So it's only really just sketches the ideas. So you're not going to learn much by looking at the, you know, the code here. But the Hitchhiker's Guide has you know, more text about it. This is just, you know, the snippets that are used there, so that, I mean, one can make sure that they compile and play with them if desired. But it shows a bit how to exploit the small step semantics to develop a you know, semantics for multiple threads. And that concludes the lecture. And so the next lecture is going to be about Hoare logic, which is going to be your second type of semantics, the axiomatic semantics. And the third one is denotational semantics, which is a bit more mathematical. It feels, or like a compiler if you're a computer scientist.